Hi guys, and welcome to this WACE Academy online lesson on the exponential function. In the previous lesson, we looked in detail about the limits of certain exponential functions and introduced you to the function of e to the x and its special properties. In this lesson, we're going to concentrate on syllabus point 3.1.4 and look at solving some practical problems in which we can use our knowledge of exponential functions. We'll just look at two example questions in this lesson. Let's get started. Let's look at a question similar to some that have been asked in WACE exams before. It says that a certain test requires that a patient be injected with a solution containing 0.5 micrograms of the radioactive material technetium-99. This material decays according to the rule T equals T0 times e to the power of negative 0.1155 T. In this case, T is the time in hours since the injection. The first question asks us to find the value of T0. The trick with these kinds of questions is to notice that T0 is just going to be the initial amount injected. We can see here that when T equals 0, we have that e to the negative 0.1155 T is just e to the 0, which is just 1. And so when T equals 0, we know that capital T equals T0. Since we know that at the time of injection there are 0.5 micrograms injected, we know that when T equals 0, capital T equals 0.5, and so therefore we know that T0 equals 0.5. Secondly, we're asked to calculate the half-life of the element. This means at what stage is the amount of material left half of what was originally injected. We already know that T0 equals 0.5 from the above, so this amounts to solving the equation 0.5 e to the negative 0.1155 T is equal to 0.25, since 0.25 is just half of 0.5. Multiplying by 2 gives us that e to the negative 0.1155 T is equal to a half. At this stage, we need to make use of the natural logarithm. You may not have encountered these yet, depending on which order your teacher is going through the course, but they're essential for these sorts of questions. I encourage you to go and check out our video on logarithms if you've not yet covered them, but I'm going to assume from now on that you've covered them. Taking the natural logarithm of both sides, we get that ln of e to the power of negative 0.1155 T is just ln of a half. But since ln just means log base e, and by the definition of the logarithmic function, this is negative 0.1155 T is equal to ln of a half. And so we get T is equal to ln of a half over negative 0.1155. Using our calculator, we get that this T is equal to 6.002 to 3 decimal places. Finally, for the third question, we have the exact same method, except this time we're setting up our equation with T equals 0.005, since 0.005 is 1% of 0.5. This means that we follow the same steps. Half e to the power of negative 0.1155 T is equal to 0.005. E to the negative 0.1155 T is equal to 0.01, and performing the same trick that we did before with the natural logarithms, we get that T is equal to ln of 0.01 over negative 0.1155, or, in other words, 39.87. So this tells us that 39.87 hours later, there will be exactly 1% of the original amount left in the patient's system. And so, since we're asked to prove an answer to the nearest hour, the answer we would provide would be 40. Now we're going to look at another example, but this time with a slightly different focus. The question says, Fermium-257 is a radioactive substance whose decay rate can be modeled by the formula P equals P0 e to the KT, where P is the mass in grams and T is measured in days. P0 is therefore the original amount and K is just a constant. The time taken to decay to half of the original amount is known as a half-life, and we're told that the half-life of Fermium-257 is 100.5 days. Okay, great. So, we want to determine the value of K. Here, we're going to use the one thing we do have an exact value for, which is the half-life of the substance. So that means that if we were to substitute t equals 100.5 into our equation, the resulting mass, that is p, would be half of the original amount. So p0 over 2. So if we set this out in an equation, we get something like this. P0 times e to the power of 100.5k is equal to P0 over 2. Now in this equation, we have two unknowns, P0 and K, but we can quickly see that P0 is multiplied on both sides. If we divide this across both sides, we'll be left with only one variable to solve for. This gives us e to the power of 100.5k is equal to 1 over 2. As in the previous question, we take the natural log of both sides in order to get at that k that we're trying to solve for. So 100.5k is equal to ln of a half. And so k equals ln of a half over 100.5. And to three significant figures, we therefore get that k is equal to negative 0.00690. So now finally, we want to look at how many days it takes for 100 grams to decay below 5 grams. Knowing values for K and P0, we now have that the mass of this substance is given by P is equal to 100 e to the power of negative 0.00690 t. We now need to substitute in a mass of 5 and solve for t, and we do this as we did all the previous questions by using our little trick with our natural logarithms. So 5 is equal to 100 e to the power of negative 0.00690 t. Dividing by the 100 first, we then take the natural log of both sides and we're left with t is equal to ln of 1 on 20 over negative 0.00690, which ends up being 434.16. Since we want to know after how many days it'll first be below 5 grams, we would answer 435, since after 434 days, it will still be above 5 grams. Finally, we want to know the rate of change on that day, and we remember that calculating rates of change amounts to looking at our derivative. So that is, we want to find the derivative of p equals 100 e to the negative 0.00690 t. We remember the fact that the derivative of 100 e to the t is 100 e to the t, and so all we need to do is carry down that factor of 0.00690 that we get if we take the derivative of the function in the exponent. Thus, we get p dash is equal to negative 0.00690 times 100 e to the power of negative 0.00690 t. In other words, p dash is equal to negative 0.69 e to the power of negative 0.00690 t. We want to find out the rate of change on the 435th day, so we simply substitute t equals 435 into the above. Using our calculator, we get that p dash of 435 is equal to negative 0.034. So on the 435th day, the rate of change is that 0.034 grams decays. These two examples cover quite nicely all of the things that you'll be required to do with examples concerning exponential functions. Calculate initial periods, calculate the rates of decay, and use derivatives to look at the rates of change. What is hopefully clear is how connected the use of logarithms is to these kinds of questions. If you're not already across your logarithms, you definitely need to be in order to deal with exponential functions. That's all from us today. Next time we'll be moving along to taking derivatives of trigonometric functions. See you next time.